All right, let's talk about the secret language of machines. You see, there's this hidden nervous system running inside everything from giant factory robots to life-saving medical equipment. And that system, that language, is called CANopen.
So just picture this for a second. You've got this incredibly complex machine. Maybe it's a huge assembly line, and it's built with parts from 10, 20, maybe even 100 different companies. You've got a robot arm from one, a motor from another, and a sensor from a third. How in the world do you get them all to work together? How do you make them understand each other without a mountain of custom code? It's a huge puzzle in engineering.
Well, the answer is actually pretty brilliant in its simplicity. You give them a shared dictionary, so they all agree on what words mean, and then you give them rules for having a conversation. That's it. And that, right there, is the magic of CANopen.
So how are we going to unpack all this? Simple. First, we'll look at why the basic CAN protocol isn't enough on its own. Then, we'll dive into the absolute heart of CANopen, its universal dictionary. After that, we'll check out the two main ways devices talk. Think public announcements versus private chats. Then, we'll meet the network's conductor, the boss that keeps everyone in sync. And finally, we'll wrap it all up and see why any of this actually matters in the real world.
Okay, first things first, let's talk about the foundation. You can think of the basic CAN bus as a perfectly paved, super-fast highway. It's fantastic for moving data traffic. But it doesn't come with any road signs, no traffic lights, no rules of the road.
You see, CAN itself is amazing at the physical stuff, getting a stream of ones and zeros from here to there super reliably. But it has absolutely no idea what those ones and zeros actually mean. Is it a temperature reading? Is it a command to start a motor? CAN doesn't know. It handles the physical connection, but not the actual application, not the meaning.
And that's exactly where CANopen comes in. It builds on top of that CAN highway, and its genius is centered around one core idea: the object dictionary. You can think of this as the Rosetta Stone for machines, the thing that makes universal understanding possible.
So every single device that speaks CANopen has one of these, an object dictionary, or OD for short. It's basically a standardized menu, a list of every single piece of information the device knows or can be told what to do. It's the official link between what the device is doing on the inside and what it's saying to the outside world.
Now, here's my favorite analogy for this. The object dictionary is like a standardized medical report for a device. You know how any doctor can pick up a medical chart and instantly understand a patient's heart rate, blood pressure, and medical history? It's the same idea. The network's master controller can look at any device's OD and know everything about it: what it is, what it can do, and what it's doing right now.
And this report is super organized. It's all structured by a 16-bit index, kind of like chapters and pages in a book. The first section, starting at 1000H, is always for basic communication settings. Then there's a big section where manufacturers can add their own custom features. But the really important part is the section from 6000H onwards. This is for standardized profiles. It means a motor from company A stores its speed at the exact same address as a motor from company B. That standardization is the whole point.
Okay, so now we know that every device has this amazing dictionary that defines what it can talk about. The next logical question is, how do they actually talk? How does the information get from one device's dictionary to another's? Well, CANopen gives them two very different ways to communicate.
On one hand, you have Process Data Objects, or PDOs. These are all about speed. Think of a PDO as a public announcement shouted across the factory floor. It's for real-time data, like a sensor screaming, "I'm at 50 degrees," over and over. It's fast, efficient, and doesn't wait for a reply. On the other hand, you have Service Data Objects, or SDOs. These are for reliability. An SDO is like a direct private conversation. It's a question and answer session, used to configure a device or ask for a very specific piece of info. It's slower, but it's a confirmed handshake.
Now, I know these diagrams are a little technical, and yeah, they're not in English, but don't worry about the words. Just look at the arrows. On the left, you see the PDO model. See how one device sends a message and a bunch of other devices can just listen in? It's a one-way broadcast. Now look at the SDO model on the right. See the back and forth? A client asks a question, the server gives an answer. It's a confirmed one-on-one conversation. That's really all you need to see here.
So we've got our dictionary, so everyone knows what the words mean. We've got our rules for conversation, the PDOs and SDOs. There's just one piece of the puzzle left. Who's in charge? Who makes sure everyone starts at the same time and plays their part correctly?
Well, every good orchestra needs a conductor, and every CANopen network needs a manager. That role is called the NMT Master, which stands for Network Management. All the other devices on the network are known as NMT slaves, and they all listen to the master.
The main job of this NMT master, our conductor, is to tell all the other devices what state to be in. As you can see from this diagram, it's pretty straightforward. The master sends out simple commands that tell a slave device when to initialize, when to get ready, when to start working, and when to stop. It's in complete control of the network's rhythm.
And there's a really clever boot-up process. When a device first powers on, it goes into what's called the pre-operational state. In this mode, it can't do its main job yet. Instead, it waits for the NMT master to talk to it, using those SDOs, those private conversations, to get everything configured just right. Then, once all the devices are set up, the master gives the command, they all switch to operational at the same time, and the concert begins.
So how does the conductor know all the musicians are still there and haven't wandered off? Through what's called error control. There are two main ways. The old way is node guarding, where the master constantly checks in on each slave, asking, "You still there? You okay?" The newer, more efficient way is called heartbeat. Here, each slave proactively sends out a little "I'm still alive" message every second or so. It makes for a much more robust and reliable network.
All right, let's zoom out and put all these pieces together. We've talked about the three core pillars of CANopen: the universal dictionary, the rules for communication, and the network conductor.
So, what's the big payoff? Well, first, you get real standardization. The object dictionary means everyone is speaking the same language. Second, you get blazing efficiency for real-time data thanks to those PDOs. Third, you get incredible flexibility to tweak and configure any device using SDOs. And finally, you get total control and rock-solid reliability because the NMT master is running the show. It's the whole package.
At the end of the day, it's this simple. CANopen provides the structure, the language, and the control you need to turn a messy collection of individual parts into one single intelligent system that just works.
It's a pretty powerful concept, right? And it kind of leaves you with this one big question to think about. What new doors open up? What becomes possible when every machine, from the assembly line to the operating table, can finally speak the same universal language? That's the future that CANopen is helping to build. Thanks for diving in with me.